Let's cover some basic examples of multivariable linear regression models. So we've already covered a bunch, and perhaps the simplest one is where we want to just minimize y minus a constant vector times an intercept, and we saw that the minimizer of this led to beta naught hat equal to y bar. And of course we can do that using our multivariable regression formula by looking at the solution beta naught hat, which should just be the Jn transpose Jn inverse Jn transpose y. Okay, so this term right here is just the inner product of a vector of ones with itself. So 1 times 1 is just 1, so we're just adding up a bunch of ones and then taking the inverse, so that's equal to 1 over n. And this is just a bunch of ones times y, so that's just going to be the elements of y added up. So that's times the summation of the elements of y, or y bar. The second case that we looked at is the instance where we have y minus x beta, where x is a vector also, squared, where we want to minimize the least squares criterion like that. This is so-called regression to the origin, and of course the regression to the mean is a special case of that, where x is just a vector of ones. And we saw already that the result of that was inner product of x and y over x with itself. That was beta hat. Well, let's just show that that agrees as a special case of multivariable regression. So we have our beta hat is equal to x transpose x inverse x transpose y. Well, x transpose x inverse is just inner product of x in the event that x is a vector, and x transpose y is just the definition of inner product of x and y when x is a vector. Okay, so two of our special cases are obviously variations of linear regression. The next one I'm going to ask for you to do on your own, because we've kind of worked on it a lot and shown it in different ways, but in the event that we want to do linear regression, beta naught times Jn plus beta 1 times a vector x. So our design matrix in this case, let me just call this trying to minimize y minus, let's say, w beta squared, where w is a vector of ones and the vector x. So, or I should probably just write it out like this, Jn and the vector x. So what I'd like you to try and show is now when you are beta hat, where beta here, again, I'm defining as beta naught, beta 1. Our beta hat is going to be w transpose w inverse w transpose y. So what I'd like you to show is that this works out to be the standard definitions for the linear regression intercept and slope. This winds up being a 2 by 2 vector, so the inverse you can actually calculate, just look up the inverse of a 2 by 2, and this is fairly straightforward to do as well. That winds up being a 2 by 1 vector. So it's a little bit tedious in terms of bookkeeping, but you can show that the just direct use of the multivariable least squares solution winds up in the same results in the 3 other cases that we spent a lot of time talking about so far. Let's consider another important special case of linear models applied in a pretty general setting. So imagine if our y looks something like this. It's y11 up to y1 n over 2 and y21 up to y2 n over 2. So in other words, our y is really equal to 2 vectors, let's say y1 and y2, of 2, where the first comes from one group and the second comes from another group. So we might think of a setting where we're plotting y and we have group 1, group 2, something like a box plot. So in some instance like that, where you're interested in modeling the fact that there's 2 groups using least squares. So we could do this with y minus, let's say, x beta minimizing that least squares criteria, where x is equal to a bunch of ones and a bunch of zeros, and then a bunch of zeros and a bunch of ones. So that, and so x has n over 2 ones in the first vector and n over 2 ones in the second vector. Now, let's work out what beta hat works out to be in this case. So beta hat works out to be exactly equal to, of course, x transpose x inverse x transpose y. But x transpose x, okay, so that's just a vector of ones and zeros, a vector of zeros and ones, times ones and zeros and zeros and ones. We want that inverse. Let me get rid of this. And then our next component is x transpose y, which is the vector of ones and zeros, then ones, then times y. Okay, so looking at this matrix, this is going to be n over 2, because when I multiply this matrix, this vector times this vector, it's going to just add up the number in that first group. When I multiply this vector times this vector, it'll just be 0. Same thing for this other diagonal, and this one will be n over 2. And there's nothing in particular about having equal numbers in the two groups. They could have been an n1 and n2 there. I just did n over 2 just in the balanced case where there's an equal number in both groups. Now let's look at this statement right here. This first one is going to be the sum of the first group, so let's just call that Jn over 2 times y1, and the second one is just going to be J transpose n over 2 times y2. Okay, and so, and I'm sorry, that's inverted, and the inverse is pretty easy because then it's just 1 over, because it's a diagonal matrix, so it's just 1 over both of those. And then so what we get is that y1 bar and y2 bar are the slope estimates for beta, which is what we would imagine should happen. If we have an effect, one for group 1 and a second effect for group 2, the likely estimate would have to have turned out to be the average for group 1 and the average for group 2. So the fitted values in this case is just going to be, if you're in group 1, it's going to be Jn times y1 bar, Jn over 2 times y1 bar if you're in group 1, and Jn over 2 times y2 bar if you're in group 2. Now, remember last time we were considering a setting where we wanted to do y minus, let's say, x1 beta, and minimize that, where x was, let's say, j n1, and then a bunch of zeros, and then a bunch of zeros, and j n2, where j is again a vector of ones. Let's say x1 is like that. And we found, so we have two groups of data, and we found out that our estimates then works out, our beta hat works out to be y1 bar, y2 bar. Okay, where again our beta is equal, in this case, to beta 1 and beta 2. Now consider y minus x2 gamma. Consider minimizing the model where x1 is equal to a vector j n1 plus n2, and then a vector that's j n1, and then a bunch of zeros. Let me just write it as 0 n2, meaning a vector of zeros of length n2. Now, so this is 0 n2, and this is 0 n1. So and this is x2, I'm sorry. and then gamma is equal to gamma 1 and gamma 2. Now notice, if I add these two columns, right, I get this column right here. And similarly, if I take this column and I subtract this one, then I get the second column here. So what we see is that x1 and x2 contain the same column space. They have an identical column space. And what we know from our projection argument is that the fitted values from both the models have to be the same. Well, the fitted values from model 1, right, if for any observation in group 1, the fitted value is going to be y1 bar. And for any observation in group 2 is going to be y2 bar. So we know that beta 1 hat equals y1 bar and beta 2 hat equals y2 bar. We know that because we worked it out in the last example where we figured it out. Okay, now look at x2 times gamma. Well, the fitted values for anyone in group 1 are now, if I multiply x2 times gamma, it's going to be gamma 1 hat plus gamma 2 hat. And then for anyone in group 2, it's got to just be gamma 1 hat by itself. So we know that the fitted values have to satisfy these equations, and they have to agree because the column space of the two is the same. So what we know then is that beta 1 hat, which is y1 bar, has to equal to gamma 1 hat plus gamma 2 hat, and beta 2 hat, which is equal to y2 bar, has to equal to gamma 1 hat. We can use that to now solve for gamma 1 hat and gamma 2 hat without actually having to go through the trouble of inverting this matrix. Now it's a 2 by 2 matrix, so it shouldn't be that hard to invert, but let's suppose you had a little bit harder of a setting, then it would be a little bit harder to invert. Let's suppose we just had 10 columns. And this is kind of a common trick in these ANOVA type examples where you can reparameterize to the easy case where you get a bunch of block diagonal 1 vectors, like in the case of x1, in which case x transpose x works out to be a diagonal matrix and then very easy to invert. And then if you want any different reparameterization, which would result in an x transpose x that's hard to invert, you can use the fact that you know that the fitted values have to be identical to convert between the parameters after the fact. Okay, so in this case, you know that gamma 1 hat has to be equal to beta 2 hat, and then you know that gamma 2 hat, then just plugging in with those two equations, has to be equal to beta 1 hat minus beta 2 hat. Okay? And so that gives you a very quick way to go between parameters in equivalent linear models with different specifications, with just different row organization. Okay? So it's a useful trick when you're trying to work with these ANOVA type models. Now let's discuss what I think of as one of the most important examples in regression. So imagine that my y breaks down into two vectors, a group 1 and a group 2, and my design matrix, which I'm going to call W, which will become clear for reasons later, is equal to a matrix called Z and a vector called X, where X is in m by 1 and Z is in m by 2. And Z looks like this. Z looks like Jn1 and then an n1 vector of zeros, and then an n2 vector of zeros, and then an n1 vector of zeros, and then Jn2. So the Z matrix looks like the two-way ANOVA matrix from previously, but we've appended an X onto it as well, an X vector. So this is the example. If we do least squares with this W, we are interested in fitting models where we have a regression line, but separate intercepts for two groups, right? So the coefficient in front of the x is the common slope, and then the coefficient in front of each z vector is the intercept for each of the groups. Okay, so we want to minimize y minus w, and I'm not going to call it beta, let me call it gamma, quantity squared, where gamma is equal to mu1, the intercept for group 1, mu2, the intercept for group 2, and beta, the common slope across the two groups. So we can write this as y minus x beta minus z, let me just call it mu as the vector of mu1 and mu2. Okay, so we can write it out like that, and then let's figure out what this works out to be. So let's use our standard trick where we hold beta fixed and we come up with the estimate for mu condition as it depends on beta. Well, if beta is held fixed, that's just a vector, and this is just the two-way ANOVA problem that we discussed previously. Remember that the two-way ANOVA problem the solution worked out to be the mean in group 1 and the mean in group 2. So the estimate for mu1, as it depends on beta, has to be the mean of this vector right here. So that has to be y1 bar, the group 1 mean for the y's, minus x1 bar beta. And then mu2, the mean for group 2, as it depends on beta, has to be y2 bar minus x2 bar times beta. Now if I were to plug those back in for mu1 and mu2 into here and subtract them off from y, what I get is nothing other than the centered versions of y. So I get y1 minus y1 bar times jn1, y2 minus y2 bar times jn2, that vector, minus x minus x1 minus x1 bar, x2 minus x2 bar. I didn't define x1 and x2, but let me just say those are just the group components of x. The x1 is the first n1 measurements of x, and x2 is the n2 latter measurements of x, and that should be times beta. Okay? So, oops, and I shouldn't say equal, it has to be greater than or equal to, because we've plugged in the optimal estimates for mu1 and mu2 for a fixed beta. Well, this is now nothing other than regression to the origin with the group-centered version of y and the group-centered version of x. So we know that the estimate of beta hat, the best beta hat that I can get, has to work out to be the regression to the origin estimate from these data. So that's just summation, let me write it out this way, the double sum of, well, here, probably the easiest way to write it out first is y tilde, the inner product of y tilde and x tilde over the inner product of x tilde with itself, where y tilde is the group-centered version of y and x tilde is the group-centered version of x. In other words, by group-centered I mean each observation with its group mean subtracted off. And you can show, and I have this in the notes, okay, and you can show, well, let's just do it really quickly here. What does this work out to be? This works out to be the double sum, let's say, over I and j of y I j minus y bar I, so I equal 1 to 2 and j equal 1 to n sub I, x I j minus x bar I, all over the double sum of x I j minus x bar I. And let me just explain my notation here. So y I j is the jth component of, let's say y11 is the first component of the vector y1, y12 is the second component of vector y1, y21 is the first component of vector y2, and so on. So we can write this out, and I think this is probably the nicest way to write it out, as for I equal 1, we can write this out as P times beta 1 hat plus 1 minus P times beta 2 hat, where beta 1 hat is the regression estimate for only group 1. If you only had the x1 and y1 data, the centered x1 data and the centered y1 data, y1 data. And beta 2 hat is the regression estimate if you only had the y2, the centered y2 data and the centered x2 data. Okay? So it is interesting to note that the slope from ANOVA works out to be an average, a weighted average, of the individual group-specific slopes, where, in this case, P works out to be the summation of xij minus summation of x1j minus x1 bar over sum, and this should have been squared, sorry about that, the double sum of x1j minus x1 bar squared. Okay, so P works out to be the percentage xij minus x bar I. So P works out to be the percentage of the total variation in the x's from group 1. So if most of your variation in your x's is in your group 1, then the group 1 slope contributes more to the overall ANOVA slope, and if the group 2 is more variable, then the group 2 contributes more, and if they're equally variable, then both of them contribute equally. Okay, so let's go back to now, once we have our beta hat, we can figure out what our mu1 hat and our mu2 hat is. So mu1 hat is equal to y1 bar minus x1 bar beta 1 hat, and mu2 hat is equal to y2 bar minus x2 bar beta 2 hat. Okay, so the difference in the means, mu1 hat minus mu2 hat, works out to be y1 bar minus y2 bar minus x1 bar minus x2 bar beta hat. Now, so and one way to think about this, the most common way to think about ANOVA, is the instance where you want to compare a treatment, say treatment 1 versus treatment 2, but you have some confounding factor that you need to adjust for. Say, for example, you're looking at a weight loss treatment, and your confounding factor is the initial weight of the person. Okay, and so if the initial starting weight of the people receiving the one weight loss treatment is different than the initial weight of the other weight loss treatment, then you'd be worried about just directly comparing the two means. Well, this shows you what, in addition to the two means, you need to subtract off if you model the data as an ANOVA model. Most interestingly is if you randomize and your randomization is successful in the sense of balancing this unobserved or this observed covariate, the baseline age, then the group 1 average should be pretty close to the group 2 average, so this difference in means should be quite small, so that whether or not you adjust for baseline weight or omit baseline weight from the model and just do straight two-group ANOVA, the estimate should be very similar. However, on the other hand, if you happen to not have had some randomization and have an imbalance so that the average for group 1 is very different from the average for group 2, then the difference between the unadjusted estimate and the adjusted estimate can be quite large. Okay, so that's ANOVA. That's an important example. I have some more written about it in the notes, but I think you can actually learn a lot about regression and adjustment just by thinking about this one example.